Okay, good afternoon, ladies and gentlemen. Once again, thank you very much for coming to this slightly oversubscribed workshop. So, good afternoon. My name's Henry Young. I'm CEO of TS Associates. I'm going to be talking to you today about low latency application engineering. One colleague and one partner with me today, David Riddoch of Solarflare, who many of you will know, whose significant claim to fame is the author of Open on Load. And I'm sure he'll tell us a few other cool things as well. And Mark Edwards, who works as TS Associates as an expert in application instrumentation technologies and techniques. Okay, who here considers themselves, in the true meaning of the word, to be an engineer? Okay, so that's reassuring. We've got at least 50% of the audience engineers. So this is something that's coming back into fashion, I believe. First of all, what's all this low latency nonsense about? I mean, this conference has got low latency in the title. A lot of the vendors outside are selling low latency technologies. So I'm sure everybody in this room will be more than familiar with the drivers behind this. The birth of electronic trading, the growth of algorithmic trading, high-frequency trading, and then competition in all layers of the financial markets between execution venues trying to attract market makers to trade on their venues and place risk on the order books. Competition between the prime brokerage service providers, all of whom want to tell their customers they're going to deliver good service, get their orders to market as quickly as possible. And also the good old-fashioned buy-side trader competition for looking for arbitrage opportunities that might only exist for fleeting moments. So all this culminates in what we all know as the latency arms race. We've seen a very significant investment over the last decade in a whole raft of technologies, all aimed at latency reduction and performance improvement. Customers who choose to outsource various functions within the trade life cycle to service providers are demanding performance transparency. They want to be able to be assured that the service provider is delivering the performance that they promise. So that's seen the emergence of a discipline that some call latency management. The idea behind it is understanding throughout the entire trade life cycle how long each stage is taking, right down to a hop-by-hop level, and thereby understanding where to invest more if you want to improve your latency, or which exchanges are providing better performance, which brokers, etc. However, to manage something like performance or latency, you need to be able to measure it. So the result of this is a fairly new discipline that's been around maybe since 2005 called latency monitoring. We at TS Associates call that precision instrumentation. We like to kind of have a slightly more engineering take on things. Okay, so let's look at some of the latency reduction techniques that have been prevalent in recent years. The most obvious is proximity and co-location. The idea of move the application to where the data is rather than move the data to where the application is. One of the current crazes is around trying to figure out how best to use microwave, a very low latency, if well deployed, but also very low bandwidth communications medium, so usually paired with fibre, and people are figuring out how to send the important data down the microwave and deal with that on an adaptive basis. We've seen a lot of vendors promoting low latency networking, low latency switches. That's a real battlefield at the moment. We've just seen Cisco, Arista, and various other firms come out with new products in that space. We've seen the upsurge of OS kernel bypass techniques used in high-performance network interface cards, something that David will be telling us about a little bit more later. And all of the middleware messaging vendors have been joining the game and providing variants of their products that use shared memory communication, LDMA, etc. So what this tells you is that there's been a lot of money spent in all the things that the banks buy in, and we've ironed out a lot of the latency. We've achieved a lot of the gains. So the remaining area to look for further gains in latency are the applications themselves. In OSI layer terms, layer 7. It's easy to buy in fast switches, fast NICs, but now people have got to actually work on their own applications. So I want to talk now about two different aspects of latency, network latency and application latency, and make a distinction between the two. So network latency is all about inter-server latency, or latency between discrete networked components in a system. That's the latency between servers, switches, routers, and firewalls. Application latency, by contrast, is what you might call intra-server latency, or within a single server. It's the latency between individual software components running within a multi-core server. These might be processes, threads, functions, even code blocks if you're interested in code profiling and code optimization. Why is application latency important? As I mentioned before, we've had a huge amount of effort invested in latency reduction in some of the lower layers, network switches, network interface cards, kernel bypass techniques to miss out wasteful operating system services, and middleware messaging solutions. So the focus is firmly, for the next few years, up in the application layer and ironing out latency inherent in applications. So what that tells you, therefore, is that application instrumentation is starting to become very, very important. The ability to measure very precisely what's going on inside applications without having a significant impact on the performance of those applications. Let's have a look at, what have we all been doing around application engineering for the last, 5 decades. The last 5 decades of computer science have been all about abstraction, making development easier, being able to ignore the machine underlying an application. So we've, over that period, we've moved from assembler to C, to C++, to Java. Apologies to Martin, somewhere in the room, but often some people say Java is write once, debug everywhere. These developments have all been about insulating the developer from the machine, enabling application developers to live in this sort of cloud where they need not be concerned at all with how their applications are actually being deployed. So that was underpinned by Intel doing a very good job of making memory and CPU cycles extremely low cost, whilst developer time became quite expensive. So the equation around minimizing development costs actually maximized application latency. So low latency application engineering, by contrast, it's about throwing away the rulebook and starting again. It's about getting closer to the machine, understanding the actual nuts and bolts of what's going on when the application executes on a particular hardware and technology stack. It's about understanding things like CPU hierarchy, NUMA. It's about choosing the right compiler optimizations, targeting the actual execution CPU architecture rather than optimizing for the development environment. It's about understanding and making good use of threading models, understanding the trade-off between throughput and latency, maybe taking advantage of specialist hardware techniques, leveraging things like GPU, which are great at floating point, but there's a PCI bus in the middle, so you don't want to have a huge amount of interaction. FPGA, technology that's great at the edge for speeding up peripheral type operations. Very, very hard work to put entire applications on, but some firms do achieve that. ASICs have been used for many years, buried inside computer architectures. It's about understanding the file systems and storage technologies you're using as well. Are you on a local versus a network? What RAID level are you on, et cetera, et cetera. So there's a lot to understand when you're actually engineering rather than just developing applications, and that's a distinction I'm very keen on making. So here are some numbers that every developer should know, and I credit Jeffrey Dean at Google, who summarized actually in a lot more detail a lot of these key performance numbers, and I've got the YouTube link on there, and this presentation will be available on the A-Team website after the conference. So on contemporary CPU architectures, a level 1 cache reference typically takes about half a nanosecond. If you're unlucky enough to hit level 2 cache, that takes 14 times longer, 7 nanoseconds. Excuse me. If the data you're referencing isn't in any level of CPU cache, and you have to reach out to main memory, typically that takes 100 nanoseconds, 200 times longer. And if your data is on disk or paged out because you're swapping or whatever, it's going to take you 20 million times longer than a level 1 cache hit. So I hope this just emphasizes why actually understanding the execution environment of an application is critically important for its performance. So I know at this stage, David, you've got a few things that you want to tell us about your take on performance engineering with applications as well. So I'll hand over to you.
Great. I just want to spend a few minutes talking about the things that I found in my experience have a really, really big impact on application performance. Now, it's a huge topic, and you could go on about this all day. So I've just selected a few important things that you should really be thinking about it, and I hope I'm not teaching my grandmother to suck too many eggs here. Do jump in with any questions that you may have. Before I dive into that, though, another thing I want to say, as we're talking about instrumentation and measurement, is that you really, really must measure whole systems. When you're looking to benchmark any piece of your application, it only really makes sense within the context of the whole application. And in my area particularly, network adapters, what that means is that micro-benchmarks aren't useless, but they're very, very nearly useless, because they're dead simple. There are no thread interactions. They sit in cache. They almost always hit the fast path. And every vendor will be able to come up with great numbers. And it'll behave completely differently when you put a technology in with your real application. And that's really what matters, isn't it? It's how fast your application goes. Okay, so back to applications. So I'm assuming that maybe you're designing an application. What are the really important things that you should think about in the architecture? I'm assuming that you've going to do a reasonably good job of making it fairly lean, not throwing cycles away here, there, and everywhere. But what the numbers that Henry just showed you mean is that it's not really about how many instructions are in your code. It's about whether those instructions are able to hit the data by going in cache rather than going out to main memory or out to disk. And there are lots of things that affect that. So assuming you've got some code that works and that it can get decent latency at least some of the time, sometimes you may find that you get high latency. You've got some jitter or you get spikes. Where are those coming from? And the answer is usually you're falling behind, and therefore you've got queuing delays, or your critical path is not running promptly, or it's getting interrupted by something. Because you've got code. If that code runs, you'll get to where you want to be fast, yeah? So if you've got spikes, it means that that code isn't running quickly, promptly in response to your inputs. Now, if you are falling behind, that means fundamentally your system isn't keeping up. You want to make it run more efficiently. Now, there are all sorts of stuff you can do, change your architecture, parallelize. Most of them are incredibly hard work and require almost a rewrite. So the best solution, if you possibly can, is make it go faster with almost no effort. And the solution to that, of course, is Solarflare adapters with kernel bypass. So very briefly, what I'm talking about there is making the network calls go a lot faster by cutting out the OS kernel, and that's what open on-load technology does. And we'll talk a little bit more about how that works later. The second thing that you can do is amortize expensive operations by adding in some batching. So rather than saying, here's a message, grab a lock, do something, release the lock, if you are falling behind, what you want to do is, say, get 8 messages, grab a lock, process all 8 messages in the critical section, release the lock. Because the locking operations are really expensive. If you can do them once per n packets, you're going to save yourself a bunch of time. Now, the next important thing, of course, is you've got to be in cache. Those numbers showed if you're not in cache, you're basically throwing huge numbers of cycles away. And I just said you should do batching. The problem is batching makes your working set size bigger in 2 respects. In your cache, by which I mean the normal sort of cache, the L1 data cache, L2 cache, L3 cache, but you mustn't forget the other really important cache, which is the TLB, translation look-aside buffer. And that's the cache that remembers your logical to physical address translations. And it's a very restricted resource, and if you overflow that, you keep having to do expensive page table lookups, and that'll slow you down massively. And that is a big deal if you're batching, because very often the representation of your messages are in buffers that aren't close to each other necessarily in terms of memory, which means you may be walking over lots and lots of pages. If you're touching lots of pages, that means lots of TLB entries. If you overflow the TLB, everything will be slow. So the solution to that is make sure you limit your batch sizes. Don't allow the batch sizes to grow indefinitely as your queues build up. Okay? And the other thing I said was, of course, you've got to keep the critical path on the processor. This is a huge, huge topic, but very, very briefly. Ideally, you want to have your critical threads pinned to isolated CPU cores. So there are lots of techniques for doing that, like ISOL CPUs and CPU sets and resource containers and all that sort of stuff. Everything else in the system needs to be moved onto junk cores so that it doesn't interfere, and that means things like hardware interrupts, SMIs, system threads, any other applications, but it also means other threads within your application. So, chances are your application has one or some number of threads which are critical path, and maybe some management threads that don't do very much that's important. You want to keep those management threads off the cores that are running your critical threads. And then you end up in a situation where, in theory, your critical threads have got isolated cores, so they should be able to run whenever they want to, and you've got some other threads that will run on junk cores and therefore are very likely to be preempted, relatively speaking, by other stuff in the system. So one serious danger that you have to look out for is you mustn't share anything between your critical path threads and your other threads. Because otherwise, for example, let's say you have a mutex that can be taken by the critical path thread and by your management thread. If your management thread happens to have that mutex and then get descheduled by something for 10 milliseconds, your critical path now cannot run for 10 milliseconds. So you're going to get a massive latency spike. Okay? So avoid sharing anything between critical path threads and non-critical path threads. The other thing is, if you possibly can, don't share your cores with multiple threads. The OS scheduler is your enemy because it doesn't understand enough to be able to do a good job. In particular, it shares CPU resources over timescales of milliseconds. So if you have multiple threads sharing a CPU, you cannot be sure that any particular thread will run within timescales of microseconds. You're likely to be waiting milliseconds if you're unlucky. Secondly, the scheduler won't do a good job of spreading load. It will tend to, given n cores for a thread to run on, it will tend to cluster threads together so that multiple of them are all running on one core and the other cores are completely idle. And it does that for very good reasons that I don't have time to go into, but the effect is that if you suddenly get a burst of load, that core will become massively oversubscribed, those threads will fight each other for time, and you'll get big delays and you'll be highly inefficient.
Henry?
Yeah.
Sorry to interrupt you. Could you tell me what you think about hyperthreading in terms of pinning threads, critical threads?
So hyperthreading is where you have two logical cores on a single core. So they're sharing execution units, they're sharing their L1 cache, but they're independent in terms of their execution. For some applications, it's absolutely brilliant, and it'll allow you to eke out an extra 20-30% of performance when they're running concurrently. In some applications, you'll do a lot better than that because it means that you can dedicate effectively a logical core to more threads. So it means you can have more threads. For some applications, it'll absolutely make things worse. And the reason is, instead of having one thread in an L1 cache, you've now got two threads in an L1 cache. So you may go from running in cache to blowing your cache completely. So it could slow you down by a factor of 5. And it's totally application dependent. I can't possibly tell you whether your app will benefit or yeah. Staying in cache is absolutely critical. We've already talked a little bit about minimizing sharing between threads, particularly between critical path threads and non-critical threads. But actually, you really don't want any sharing between critical path threads either, because inevitably sharing state between threads means you're going to cause cache line bouncing. I've already said you really want each thread to be on a separate CPU core. So if threads are sharing state, that means you're moving state between cores. That's expensive. Now, obviously, that applies to things like data structures in memory. mutexes, but there's also a whole load of state that you're not seeing that's hidden under the APIs that you're using, and in particular, in my case, networking. If all of your threads are doing sending, receiving on the network, they're probably all colliding somewhere when they get close to the network interface, sharing state, sharing locks, slowing each other down. And this is an area where kernel bypass technology can help you again. You'll see why a little bit later on, but essentially you can dedicate resources on a per-thread basis so that they don't collide with each other until they get to the hardware layer. And I should say, hardware is very, very good at multiplexing. It's really software that does a bad job. The other thing, of course, is avoid thread hops on the critical path, because inevitably that means sharing state between threads. The exception to that, of course, is if you can't get everything done in a single thread just because there isn't enough grunt on one thread, you may have to move work out from one thread to another, and that's just life. The solution to that, of course, is try and do less work or spread the load out at a higher level if you can avoid it. The sooner you can spread the load out, that's usually better. And if ideally you want the load spreading to happen at the hardware layer. And of course, avoid other context switches such as interrupts. Two reasons. One, of course, they're taking away CPU time. Second reason is they're polluting the cache because they're doing something, bringing more data into cache, which is pushing your data out. So the other thing about cache is not just avoiding sharing and cache line bouncing and that sort of stuff. You've also got to keep your cache warm. Now, this really applies more to the branch prediction cache than it does to the other caches. So what I'm saying here is, I'm assuming you've done everything I've already said. You've got a single thread per core. You've isolated it really well. So really, there shouldn't be much running on your cores than your critical thread. But you've not got anything to do. You're waiting for some interesting event, like a market data signal, before you can trade. And so you're maybe only trading once a second. The problem is that your code path that does that trade is only running once a second, and in between times, all of the good state that's built up in the branch predictor, and to some extent at the other caches as well, is lost. And as a result, your critical path runs several microseconds slower than it otherwise would. And the only way you can deal with that is either manufacture fake work to do, ideally, in fact, manufacture real work to do, and do it relatively frequently, at least 10 times a second, maybe 100 times a second, and that'll keep those paths alive. But the key thing is here, you're talking about the branch predictor, right? You can't have any conditionals that say, if this is dummy work, do this, else do that. Because every time you have a conditional like that, it's pushing the branch predictor the wrong way. Okay? So the key thing is, try and make it so that you can make your dummy work look as much as possible like real work, but then have one conditional at the end that says, no, not really, I was only pretending. Okay? And that, by the way, very much includes the network portion. So if you possibly can, you need to actually push out a packet onto the network, because otherwise you're missing out all of those code paths that go through my code, and those will all be out of the branch predictor as well. Okay, so that's just a few tips. Back to Henry to talk more about instrumentation.
Thank you, David. How do we do application instrumentation? There are various techniques that have been prevalent. Code profiling, where you ask the compiler to build a special build of the application that instruments each function call boundary with some additional instructions and persists some information about the timing at each of those function call boundaries. The problem with that approach is you generally find the application runs much more slowly, and if it's an application that needs to interact with the real-time environment, as many of our applications typically do, it kind of doesn't really work. You can insert code into your applications to get the current time and write information out to a log file maybe, or persist it to some shared memory to be picked up by another thread at a later stage. Again, that's pretty invasive because you're putting a lot of code in line with your real code, so you slow down. You can read the TSC register on Intel CPUs, and that's a very, very quick operation. But the problem there is there's some challenges around understanding how that's synchronized across different cores, or even how time is synchronized across different servers. So the key message about traditional software instrumentation techniques, pure software instrumentation, is don't pull time up into the user mode application. Push your event down into the kernel, and ideally down to some kind of specialist timing hardware. So we realized that this is a very, very useful technique back in 2008, and came up with a new concept that we call the application tap. And we called it the application tap because at that time, the idea of using network taps to tap into messages within networks was quite well established. And really, we were designing this capability to tap into applications and be able to harvest information from the core of applications with the absolute minimum practical performance impact and with very great precision. So unfortunately, that manifested itself as a piece of hardware that has to be plugged into your server called the application tap. And it's a PCI card. On here, we've got an FPGA sitting under that heatsink. We've got an RJ45 port there dedicated for PTP time synchronization. And then running on the FPGA, there's a 10 nanosecond resolution clock, which you can keep synchronized with the rest of the world realistically to maybe 0.1 of a microsecond in a very well-engineered environment. And the idea behind the application tap is you're provided with an instrumentation API that enables you to put instrumentation hooks into your code. So, for example, you might be writing an order matching engine and you want to be able to find out the precise time of order match event, or a gateway and discover the precise time when an order has passed certain validation tests, for example. So that API will be triggered when the event occurs and pass some useful metadata down to memory sitting on the application tap card. That is timestamped by the FPGA firmware very, very precisely, and then pushed out of one of these network interfaces as a network message containing the metadata, the event identification information, and the precise timestamp. And that can be collected along with similar cards sitting in other servers, and also decoded messages that have been timestamped via more traditional latency monitoring type devices. So the idea is it gives you the tools to enable software event instrumentation with minimal performance overhead and far greater precision than would be possible using the operating system clock. So this was effectively the first generation, the first manifestation of the application tap concept. Typical uses, we originally developed it for software component latency monitoring. So the idea there is being able to measure latency hop by hop at the inter-server level, at the network connected component level, is quite a developed concept. But the idea of being able to drill down to software components, individual processes communicating via shared memory, etc., on a multi-core server, the traditional techniques are not adequate. You can use this for precise timing of application events. Some people use it in a development context for code profiling, deterministic code profiling as we call it. It's a building block for what we call logging offload, the idea of offloading both the CPU workload of traditional logging and also providing far more accurate timing for log messages. And also we're starting to look at how this can be applied for more traditional application performance management in a cloud environment. So the concept there is you throw an application up into the cloud, you can't see it anymore, broadly speaking. So if we look at how the application tap concept works, if we look at conventional software instrumentation, you would typically put code in your application that might trap some kind of event, make a function call, get time from the operating system, which, depending on which kernel version you're running on, can be quite a fraught experience, and Mark's going to tell us a little bit about that in a moment. Persist that information in some way, and then typically you might need to do some kind of correlation between different events happening in different locations to extract application latency information. With the application tap, this reduces to the workload within your application, simply making a single lightweight function call. And then the FPGA card does the precise timestamping, the message packing to transmit the message, network offload, and then the correlation workload to calculate latency is done on a completely separate device. So you achieve a lot of CPU offload and a very significant improvement in event timing, typically up to at least a factor of 1,000, if not 10,000, depending on your clock engineering. That was originally back a few years ago. More recently, we've been kind of building out the application tap ecosystem to support it on a number of different hardware platforms, because we appreciate requiring people to have to go and plug in a dedicated PCI card where their equipment might already be deployed, or they're running on a one-use server that doesn't have a spare slot, is potentially problematic. So we've more recently integrated the application tap concept with the latest generation of Solarflare 10 gigabit network interface cards. If we then look at how the original app tap looks compared with the Solarflare implementation, there is a little bit more software work going on that's demonstrated by the larger proportion of purple here. So purple is work done in software in the context of your application, and then the green is work done in hardware. So what we now have is a lightweight function call to an API. We're getting operating system time, but there have been some improvements in modern kernels in terms of how quickly that can be done, doing a bit of message packing, and then taking advantage of the network offload provided by the ASIC on the Solarflare card via open onload or an underlying API. Okay, so when we originally developed the application tap concept back in 2008, operating system time was generally inaccurate. It was very expensive to fetch, typically half a microsecond, and network transmission was quite an expensive operation, typically involving more operating system work, kernel bypass in those days not being particularly prevalent. So the recent developments that make integrating the application tap API with Solarflare cards more practical is that a lot of firms are looking at synchronizing their operating systems more accurately, typically using PTP, and indeed there is a PTP version of Solarflare's technology available, precision time protocol, incidentally. The Linux kernel has sprouted this new feature called VDSO, which basically means that getting the current time from the operating system is effectively more or less a memory read rather than a lengthy system service call. And we're able to leverage Solarflare open onload, enterprise onload type technology, a particular underlying API called EFVI, which enables us to send data to the network very, very efficiently. I'm going to hand over to Mark now, who's going to tell us a little bit more about how this works and a very salutary lesson on how long it takes to get time from an operating system, depending on which kernel version you're running. Thanks, Mark.
Thank you, Henry. Right. Welcome, everybody, to my 3-hour workshop on application instrumentation. Oh, we must be in the wrong gig here. I'm not allowed to do that one, am I?
10
no.
minutes max.
Okay, right, okay. Right. As Henry said, we have expanded the application tap ecosystem away from talking specifically about talking to a PCI card and into several more arenas, of which the one we're talking about today primarily is the emulation of the application tap card through a software emulation over the top of Solarflare's EFVI technology to offload the network stack. So we saw the earlier diagrams, and we've also had mention in earlier slides of trade-offs between the latency and throughput. Here's an expanded slide from the previous breakout. So we got the purple, which is going on inside the host, and we can effectively split it into two to cover the two different functional requirements of what we need. When the application is calling us through our API function call, we need to be very low latency, as low as we can get. We want to return like that. But because this is a software implementation, we do need a couple of things. We need to take the timestamp from the host, but pushing that out to network is going to be expensive directly inside that operation. So what we actually do is we copy all of this information, or put it directly into internal buffers, and we can actually have a background thread that doesn't need to be generally high priority or anything like that, because the fact is we've got the metadata that includes the timestamp, so if it takes a second to send it out, who cares? The comparison is done on the remote end. So our background thread is just waking up to service internal buffers, where it will do the heavy lifting work of message packing, and then regain some of the benefits there by using the Solarflare EFVI interface, which we've found to be incredibly efficient, because we can actually quite easily, with reasonably smallish payloads, we can max out 10 gigabits a second through that background thread. But that's not what I'm talking about today. Just thought I'd put that there so we understood. This service is our throughput requirement. Now we have a requirement here of understanding the low latency that's going on through the system. So we coded all of this up, or I coded it up, but we have a lot of engineers here. When you finish hacking a bit of code from some early principles, what's the first thing you want to do with it? You want to channel your inner Jeremy Clarkson. What's the question? How fast does it go? What's the speed? So I found myself a very battered piece of hardware. Battered hardware is great. Nobody steals it from you. So what that machine had, it had a bunch of disks. It was a standard Dell 710 server, a Halem chip, 16 cores, reasonable amount of memory. And we were projecting that we were going to be selling this or promoting this from Linux kernel versions that supported VDSO and not below. So we're ostensibly saying we're going to support from 2.6.18 upwards. And at the time we were wanting to do this testing, seemed a good idea to look at what's the latest kind of research kernel out there, which was Fedora 17, and that was the 3.5.4 kernel. I haven't tested it on any of the newer ones that have come out since. I think we're up to 3.7.2. And we also chose some interesting point releases in between from various versions. And when we crunched all of those numbers, we charted them, and what were we going to expect? Between the best and the worst case, possibly, I don't know, 10% difference in performance. Just the only thing that's different, they're all running on the same piece of hardware. It's just the Linux kernel version, or the version of distribution of Linux that's different. Here we go. We get a good case where we can reach over 8 million events per second that we process through our low latency context that we want the application to that the application calls. Worst case, 800,000. It's not a 10% difference, it's a 10-fold difference. That is, well, frankly, we were shocked. And we wanted to explore that a little bit more. What's causing that? Why? I'm willing to admit I write code as badly as anybody else, but the only thing that's different is the environment it's running in. It's not my code, it's the same code each time. Now, if we went backwards, section there, what's going on here? Well, we essentially only have two things we're doing in this low latency context. We're reading the OS timestamp, and we're doing some data copying. Now, although we expect a few bits of difference between the Linux versions, I don't expect a memory copy to be 10 times slower on the same physical host with different versions of the kernel. So the thing to investigate is obviously the timestamp. What is happening with the timestamp that is causing this difference in the figure? So we went away, rejigged the benchmark test to kind of profile what was going on at the timestamp. Now, there are three things we looked at. The standard call most of you are familiar with, get time of day. That's the traditional system service. There's a problem with that as far as we're concerned. It only reports in down to microsecond component. That's not good enough for us. As you can see, if we're doing 8 million events per second, we're issuing, if we were only using get time of day, we'd have non-unique timestamps on tens or even hundreds of events. So we have to use the what became the newer system called the clock get time, of which there are a couple of variants, and that gives us nanosecond components. So we actually tested 2 variants of the clock get time and used a base reference with get time of day, and did this again on all of the 5 variants. Here's the figures. 2618, get time of day. Well, that looks quite reasonable. 67, 70 nanoseconds to make the call and return. Well, we can understand that quite simply. That's VDSO. It's just a memory read. So there's a few bits and pieces around it, probably, but essentially a memory read. So why is clock get time 5 times slower? Okay. A little bit of hunting around. We can read the thread statistics, thread CPU times, and we actually find that in 2618, clock get time, whichever call, is making a ring transition down in a kernel. So it's not actually hooked into VDSO. It's still a different code path and a different set of code. Then the real shockers, 2624 and 2627. 10 times slower. There's your culprit. Get time of day is suddenly taking 600 nanoseconds. If you think that go back, we were 800,000 events per second. That means the latency of our API call before we return to the application is about 1.2 microseconds. So 600 nanoseconds are taken up just simply reading the time, and mind you, there's about 500 nanoseconds unaccounted for somewhere, which are probably unaccounted for with some of the reasons David was talking about just now. Whether it's slightly gratifying is that we actually now see some consistency across the values for reading the timestamp, whichever value it is. Turns out now that they're actually all reading the same memory locations. They're operating on the same internal algorithms. There are some various bits and pieces that go on there because you've got the hardware interrupt is non-maskable and various other bits and pieces are going in there. And I assume that I haven't actually looked at the code. I should do sometime, but there'll be mutex locks and all sorts of things going on down there. Now, somebody thought that unifying the timestamp code and maintenance of time in the Linux distribution was a good idea, but they made a bit of an error, didn't they? Somebody, when they came to 2632, which is kind of a Red Hat 6 distribution level, decided to fundamentally rewrite it. And look at what a difference they made. 2632 is down to about 45 nanoseconds, and the Fedora distribution at the research kernel is down to 35. And I would suspect the latest ones maybe even slightly lower than that. That's a factor of 15 and a factor of 18 slower than, or smaller than the worst case. We are now suddenly getting some serious effort in the timestamp. It's now almost a negligible component of what we need to do in order to be able to do timestamping on the host. We can talk about the actual accuracy of that timestamp and the variability of it, but that's kind of a 3-day workshop in its own right. So we'll park that for the time being. So the moral here is that we've talked about application and latency engineering by looking at offloads, hardware offloads, all the things that we as latency engineers are kind of conditioned to look for in solutions that can start getting quite exotic. Take a step back once in a while. Have a look at the host system services you're calling. We take these for granted, but the fact is somebody else actually wrote that code for us. Why should we take it for granted? They can be as bad as programmers as we are, and they can screw up, and we've just seen that they royally do screw up at times. So the moral being, you don't necessarily have to look or see some expensive solution. This is actually low-hanging fruit you can get for some of your applications if you're looking at using timestampings for yourself, not necessarily just through our side of things. The low-hanging fruit, if you're stuck on some of these earlier kernels or versions, try looking at other system services in the newer kernels. They may have got worse. Code evolves, and sometimes it evolves badly. But generally, in the long run, the evolution is going to give you some significant performance improvements. So as I wrap up, just go back to, I'd like to revisit this chart. Because now by understanding where our latencies came from, that we had to really understand the code in the low latency context that was being used, let's look at this top performance level. We see the bar charts that events per second decreases smallly but linearly as the event payload size increases. So at 4 bytes payload, we've got 8.2 million, and at 60 byte payload, we're around about 7.4 million events per second. And if you wonder how much data that is that's actually being pumped out the other end, in network terms, that's around about 520 megabits. For actual application data that's going through, it's about 460 megabytes a second. So the point of this line is, what are we seeing? We're seeing things slow down ever so slightly. But we now know from our investigation that the timestamp is actually, on average, at least on average, is a constant of quite a small component. So what's this factor? Well, there's only one other thing we're doing in that thread. We're doing a mem copy. So what we're seeing now is we're seeing a signal in the data that shows us how long an extra D word of mem copy is taking in our latency system. We have now got some very significant resolution of the data, of how the data is being performed in our, at least in our level, and how we interact with the application. So that's kind of my story with that I'm kind of proud of with the Solarflare, but it came about by an interesting latency problem, and that's our story of how we solved it. Thank you very much.
So I'm just going to take a few minutes to talk about how the network adapter bit does kernel bypass and why that helps, and the features of the adapter that make this stuff possible, but also help your applications go fast. So as you can see, huge range of adapters. I'm not going to bore you with all the details, except to just point you at the one at the bottom here, which does all of the smarts that the other ones do, but also slaps on a big fat FPGA to do all sorts of extra clever stuff that possibly that we've implemented for you, or possibly you want to implement yourselves. 4 o'clock in the Fleet Room, going to be talking about that in more detail. So the first feature of our products, and probably the most important, is the ultra-low latency and ultra-high performance that you get with a kernel bypass. And this diagram shows how that works. So here's your network adapter down here. This is your OS kernel. And the way networking normally works is you've got a device driver in the kernel that talks to the hardware. You've got a network protocol stack here. Your applications talk to that through the sockets API. And here's your application. Now, if you're using kernel bypass, what changes is that you get a dedicated route to the hardware so that you can talk to that bit of hardware without having to multiplex through the OS. Because it's dedicated, it means you haven't got to share it with anybody. As we said earlier, sharing is bad. Apart from that, everything else stays the same. So your application doesn't change. You're still talking to the network through the regular sockets API, but what's different is that we've chucked this bit of software here into the user-level process. So this is really just a library that intercepts your networking calls and executes them at user level. And your entire critical path, most of the time, operates at user level, cutting out this lot. And that makes a big difference. Basically, it saves you a whole heap of CPU cycles. That cuts out a bit of latency, and it massively increases the message rate that you can achieve. The importance of increasing your message rate is that you're much less likely to fall behind, which means you're much less likely to get the queuing delays. How much do we reduce the CPU cycles by? Well, for sending and receiving small messages, it's about a factor of 5 improvement. As I said, you don't have to change your apps. This technology is binary compatible with existing apps. It just uses the regular BSD sockets API. So it works with your code. It works with third-party code. You don't need to have the source. It just intercepts stuff at the binary level. It uses standard protocols. So you can put this technology on one of your servers, but not the other servers. There's nothing changing on the wire. And, of course, it's regular Ethernet. So you can use anybody's cables, anybody's switches, all that sort of stuff. See, slots in nicely. Incidentally, it's open source, and of course, we provide support and all that sort of stuff. I'm only going to show you one performance chart, and this is the one that I think is the most interesting one. On the x-axis here, what we've got is message rate in millions of messages per second, so going from 0 to 5 million messages per second. And on the y-axis, you've got latency. This is application-to-application latency from one server to another. And what we're doing is we're sending messages from one box to another at all of these different rates and measuring how long it takes to get there. So it's one-way latency. And the blue line is what you get with kernel bypass, open on-load technology. This is what you get with the OS kernel, the traditional networking stack, and that's using 2 CPU cores. And this is what you get with the kernel stack if you're using just 1 CPU core. This is, of course, using 1 CPU core. So the fair comparison really is between the blue line and the red line. And obviously, you're getting better latency, but you're getting much, much higher throughput. This guy's maxing out at about 700,000 messages per second on a single core. This guy will do 4 million messages per second on a single core with about 6 micros of latency. And you're at 2 and a bit micros latency down at the bottom end. OK, now, what about if you want to do the app-tap stuff? Well, this is how it works. Essentially, the hardware has many 1,024, in fact, of these virtual NIC instances. And a virtual NIC is essentially an interface for sending and receiving packets at the raw Ethernet layer. And each software context that wants to do some networking gets one of these of its own. So every application that's doing open onload gets one of these. Or if you like, every thread that's using open onload can have its own one of these. The OS kernel gets one of these, so it can do its sending and receiving. And then, of course, we've got the AppTap emulation here, which is using its own VNIC interface. And that basically means that this can work without having to interfere with the kernel, without having to interfere with open onload. You can use all of those things at the same time on the same system. The other feature that we need for the AppTap emulation is that we don't just want our timestamps to be cheap, we want them to be right. And we want to be able to compare them between servers on the network. And that requires that we synchronize the clocks on all the servers in our network. And you achieve that using the PCP Precision Time Protocol. 2 of our adapters, the 5322 and the 6322, are just like the other adapters, except that they add hardware timestamping of PCP packets and a precision oscillator. And those 2 things together mean that you can synchronize the clock on your server to around 200 nanoseconds. So, and in fact, I mean, we guarantee you'll get 200 nanoseconds. Some customers get much better. Some of them report 50 nanoseconds. So basically now, any timestamps that you take on your server, whether you report them in your own logs or you send them via the AppTap API, those are now accurate, synchronized timestamps that you can compare not just between threads, but between servers throughout your network. And if you've done PTP synchronization with a UTC synchronized master, you can also compare those timestamps across sites as well, perhaps compare them with timestamps from your exchange or different sites across the world. This is the last slide. This is just a plot that shows the error that, between a master and a slave. And in this case, you can see we've got a spread of around 50 nanoseconds between the master and the slave. How do we measure this? How do we know that that's what our error? The answer is, of course, we bought a couple of regular AppTap cards from TS Associates, one on the master, one on the slave, used those to measure the clocks between the 2, and that's the answer they gave. Thank you very much.
Okay, we're wrapping up very soon and opening the floor to questions, so get your thinking caps on. We've been given permission to overrun by 10 minutes, I believe, so I'm just going to wrap up. I think this is the last slide. So application tap for Solarflare. Before this was made available, if you'd wanted 10 gig Ethernet PTP clock synchronization and application tap instrumentation on a server, that would have required 3 separate PCI cards, which already means you're constrained to using 2U form factor or above. So what this innovation gives us is the ability to provide 10 gigabit, high-performance, low-latency 10 gigabit network functionality, PTP time synchronization, and application tap instrumentation on a single PCI card. So it's pretty convenient from that perspective. So the application tap ecosystem now consists of our own very highly accurate, very deterministic PCI card, the Solarflare version, a pure software emulation version, which is great for developers or deployments into colos where you don't care about timing because the exchanges are so slow it doesn't matter. There's a remote daemon version that we can tell you about. It's also convenient for certain types of deployments. And the idea is you have a single instrumentation API that you can choose to deploy in a number of different ways that enables you to trade off between precision, performance, deterministic behavior of the instrumentation API, PCI slot availability in your servers, and cost. So thank you very much for listening. We can take questions.
What's the trade-off if you decide to use software at TAP with, say, a 63 or 5322 NIC from Solarflare? So you've got the hardware precision, timekeeping, that's training the OS clock, and you choose to use the software app tap, that can't be as precise and as accurate as the hardware app tap PCI card.
Correct, yes. So you're basically trading off time precision with performance and cost. So the pure software version is actually, we don't charge for it. The hardware version using our dedicated FPGA card that gives you the best possible accuracy and the best possible deterministic behavior on the API call, which is very important in certain situations, is the highest cost option. And the Solarflare implementation sits in the middle with decent accuracy, particularly if you're using PTP, a little bit more performance overhead because more of the work is done in software than hardware, and much lower cost. Did I already say that? So that's basically the kind of trade-off equation when you're figuring out how do I deploy this. Do I need the best possible accuracy and deterministic behavior, and I only need a few of them so I can buy the expensive solution, or am I doing a mass deployment in production where I'm not so concerned about using up a few more CPU cycles, I get great performance because I'm transmitting at 10 gig rather than 1 gig, and I get the convenience of reusing hardware that's already on my servers.
Can you say what the delta is between precisions?
Well, pure software emulation will depend on how well synchronized your OS is. The precision with both the, well, Mark, do you want to answer that actually? You've been doing some work on that.
Yeah, well, in actual fact, the pure software and the Solarflare emulation both have to use the host timestamp. So they are affected to a degree with regards to the version you're running on and the host clock. There's also a case that if with the Solarflare emulation with the PTP enabled, you've got pretty good accuracy with regards to that. There are, I think I said earlier that I could do probably a 3-day workshop on the variability within the timestamp. So we would potentially say that there is 10 nanoseconds on the hardware because we guarantee the clock on that is guaranteed. It's run with our own FPGA. We know what we're doing, and there's nothing else involved. Once you're up into software, especially in user mode, lots of things come along that David has touched on. There's thread scheduling, thread switching, interrupts, context switch, you name it. So if you tune your system, you could probably get a reasonably good, I don't know, couple of hundred nanoseconds, reasonably accurate. Beyond that, if you're leaving the operating system to run by itself, then I'm loath to give a figure and say that all bets are off, because some of the an interrupt comes in that takes 10 milliseconds. Okay, so you need to isolate your cores, make sure you're the only thing running, doing whatever. So there's potentially a workshop we could run together for several days that would have to answer that question.
Mark loves doing workshops. Okay, I think we've got time to take one more question. It's a question at Bill. Two more? Okay.
Henry, I'm just curious. You've mentioned a lot of TS associates, etc. What about CoreLex? Are you guys integrating that technology now, or is that part of
that's
what
a
you're
slightly
doing?
out of band question, but yeah, I mean, you're referring to the fact that we acquired CoreLex last July, and we're supporting both products on an ongoing basis. We have some good customers. We're about to announce the release of CoreLex version 5, which has some pretty good performance improvements and features that we'll be detailing in due course. And we're in the process of taking the best parts from our existing tip-off latency monitoring product in CoreLex and cross-fertilizing the two, cross-fertilizing decoder libraries, etc. Thanks for feeding me that question. It wasn't pre-arranged. Yeah, we've got a question at the front there.
Hi there, it's Anthony McGee from Advert Optical Networking. I'd just be interested to understand the numbers that you were quoting on the PTP accuracy side when you said 200 nanoseconds accuracy between a master and a slave. Have you looked at the implication of the number of hops that exist between the master and the slave, and also what kind of dependency is there on asymmetry in the delay path?
That's a very interesting question. Yes, asymmetry does affect the accuracy of PTP. In fact, it limits the accuracy of synchronization that
asymmetry causes a constant offset, which means your time will be wrong by a constant amount. You can measure that using PPS, and once you know what that constant offset is, you can configure the PTP daemon to correct for it. So the important thing is, particularly if you have a speed change in your network from, say you have a 1 gig master but a 10 gig network otherwise, that means you have a higher latency from master to slave than vice versa. That will give you an asymmetric path. That'll give you a constant offset. You just need to measure it and correct for it. The other big thing that's important is jitter in the network. And if not corrected for, jitter in the network will cause inaccuracy in your synchronization. The solution to that is, well, partly having a hardware having the stable oscillator on the card allows the Solarflare solution to filter out some of that jitter if it's there. But the gold-plated solution is you need a switch that has PTP support in it, either boundary clock or transparent clock. And that means that the switch itself will correct for any jitter in the network.
There's one other very important thing to understand about PTP, particularly compared with NTP. NTP, as a standard, defines a protocol and a slave and error recovery algorithm or time recovery algorithm. With PTP, PTP only defines the protocol, not the time recovery algorithm that runs at the slave end. So what you've got to do is be very careful about the type of algorithm you choose. And basically, there's a trade-off between convergence time and susceptibility to jitter. So if you're running in a LAN environment, you'll typically use a time recovery algorithm that converges very, very quickly, but is quite susceptible to jitter. And in a LAN environment, hopefully you don't get much jitter. If you're operating in a WAN environment, you want to use a time recovery algorithm that uses a much greater time range of information and therefore converges much more slowly, but gives you much better accuracy. And so, for example, when we're shipping PTP time synchronization on our products, we distinguish very carefully between WAN optimized and LAN optimized and actually use different PTP vendors' products in each of those use cases. Okay, I'm being given the wrap-up signal. We've overrun by our permitted time due to the room reorganization, so I'd like to thank you once again for attending our workshop.